Hello guys, welcome back to another video, and this video will heavily build upon the infinite series that we sort of derived in the last video. The integral in question, labeled as I, is from pi over 4 to pi over 2 with the natural log of tangent of x. When I write natural logs like these, I mean they're nested. This, I would like to point out, is a special case of the family of integrals known as the Malmsten integrals, which are defined as integral from 0 to 1 of a function of x, p of x, over q of x, times natural log of 1 over x dx. Now the integral in y that we have is a special case, is called the Vardi integral, because you can convert this into a general form of the Malmsten integral by doing the appropriate substitution, which in this case is 1 over x equals tangent of x. So let's try to evaluate this. The logical thing to do is set a u substitution, u equals natural log of tangent of x. That gives us e to the u as tangent of x. And then du is simple, is secant squared of x over tangent of x. This is just the chain rule that I'm doing here, which I can simplify because secant squared is 1 plus tangent squared x over tangent x dx, which becomes, because e to the u is tangent of x, 1 plus e to the 2u over e to the u dx, that is du. And then a simplification is natural here, which is e to the u plus e to the minus u du. That changes our integral from 0 to infinity. You can evaluate that easily of the substitution. Natural log u over e to the u plus e to the minus u du. This becomes e to the minus u natural log u over 1 plus e to the minus 2u du. Now we can use the infinite geometric series formula to sort of get rid of the denominator, because we hate denominators in integration. And then we shall have the infinite series part, k equals 0 to infinity minus 1 to the k e to the minus 2uk du. Now there's a theorem in real analysis. A power series, like the infinite geometric series is, in its radius of convergence, is uniformly convergent. So that means that we can shift it inside and outside integrals, like integration of the terms before summing and after summing is the same. So we really haven't lost touch with the function it evaluates, the value it evaluates to, before or after. That's the way I like to interpret this. Because if it's not in its radius of convergence, then we sort of have lost its analyticity, which means, it's no longer in touch with what it converges to. Like whatever it converges to inside its radius of convergence is not what the series evaluates to outside its radius of convergence. It can be something else, or it can just diverge. And the integral itself, by its uniform convergence, is also uniformly convergent. So that helps to pull the infinite sum outside. I don't really write such a big justification every time, but I think I should do it this time. So sum goes outside. All the purely k dependent terms go outside. Everything else can be kept inside. You can group the exponentials up like that, and then with the natural log of u du. Then if we set t to be 2k plus 1 times u, dt to be 2k plus 1 du naturally, we shall end up with sum k equals 0 to infinity minus 1 to the k integral e to the minus t, I think, yes, we don't need the u anymore, t natural log of t over 2k plus 1 dt over 2k plus 1, which we can just do some simple algebra on. So the exponential is as it is. We can probably pull out the 2k plus 1, and we shall have in brackets, we can split the natural log up, natural log of t minus natural log of 2k plus 1 dt, and now we shall have two integrals here. So there's one from 0 to infinity e to the minus t natural log of t dt minus sum from 0 to infinity minus 1 to the k 2k plus 1, and we can probably pull the natural log outside. Sorry, we're running out of space on the right side there. Maybe I should move things around. The dt there, yes, that's right. Now, if you see just the integral here, and maybe I can use my my highlighter pen, my pointer pen. This is the digamma of 1, which is minus Euler-Mascheroni constant. Meanwhile, I shall write what the infinite series is. So let's choose a different color. So the infinite series here, minus 1 to the k over 2k plus 1, is actually a special case of the Taylor series for the arctangent. Then this becomes the arctangent of 1, which is pi over 4, also known as the Madhava series. So we've basically sorted out the very first term that we have there. The first part is pi over 4, and then this is the digamma of 1, which I've made several videos on. This is minus Euler-Mascheroni. And we can simplify this a little bit. So we can take this minus in, and then we can change the index from k to k plus 1 over 2k plus 1, natural log of 2k plus 1, and then this integral is just gamma of 1. This integral is just gamma of 1, so that's 1. So forget that. Now there's one more thing we can do. Notice the very first term here is when k equals 0, we have natural log of 0 plus 1, natural log of 1, which is 0. So the 0 term is just 0, so we can just drop that out. and we get minus pi over 4 gamma plus sum from k equals 1, because we dropped the 0 term, to infinity minus 1 to the k plus 1 natural log of 2k plus 1 over 2k plus 1, which I shall call S. And evaluating S is why we needed the last video for. So I'll show you in a bit why that is the case. Now let's recall what we had before from the previous video. So let's recall that we had 1 over pi sum from n equals 1 to infinity sine of 2 pi nx natural log of n divided by n was natural log of gamma of x minus 1/2 natural log of 2 pi plus 1/2 natural log of 2 sine pi x minus 1/2 gamma plus natural log of 2 pi times 1 minus 2x. Why is this connected to the s we have there? You'll see we have the natural log and we have a sense of the denominator. Let's try to fix a value of x. So if we set, I'm trying to choose a better color, x to be 3 over 4. Let's see what that does. This is purely trial and error. 1 over pi sum from 1 to infinity. We have sine of 3 pi over 2n natural log of n over n equals natural log gamma of 3/4 minus 1/2 ln 2 pi plus 1/2 ln 2 sine 3 pi over 4 minus 1/2 gamma plus ln 2 pi 1 minus 3/2. Let's before simplifying the right hand side you'll see is, so for n equals 1 it's 0 because natural log of 1 is 0. N equals 2, well, for that we have sine 3 pi, which makes everything 0. N equals 3, we have sine of 9 pi over 2. If you remember, your trigonometry is 1. N equals 4, sine 6 pi is 0. N equals 5, sine 15 pi over 2 is negative 1. So you see the even ones are going out. And we only have the odd term starting from 3. So we can generally write this as 1 over pi sum from n equals 0 to infinity of minus 1 to the n plus 1 of natural log of 2n plus 1, because otherwise how else would you generate the odd terms, over 2n plus 1, because now if you plug in n equals 0, you're going to have a 0. So that sort of rules out the n equals 1 or n equals 0 term. In this case n equals 1. N equals 1 will give us a 3 everywhere. So that will sort of generate the positive here. So we fixed all the signs, you can check. If we want to eliminate the 0 term, then all we have is 1 over pi. I would suggestively label this as k minus 1 to the k plus 1 natural log of 2k plus 1 over 2k plus 1, which is cleverly s over pi. It's s, but we got the extra factor of pi in there. So this is s over pi. There we go. Our left hand side is simply s over pi. This simplifies all our calculations significantly. With natural log of gamma of 3/4 minus 1/2 ln 2 pi plus 1/2 natural log of 2 times sine 3/4 is 1 over root 2 plus 1/4 gamma plus ln 2 pi which just becomes pi ln gamma 3/4 minus pi over 2 ln 2 pi plus pi over 4 ln 2 plus pi over 4 gamma plus ln 2 pi, which can be simplified to give pi ln gamma 3/4 minus pi over 4 ln 2 pi plus pi over 4 ln 2 plus pi over 4 gamma. So finally, we can write what I was. I was minus pi over 4 gamma plus s, and s is evaluated above, pi ln gamma 3/4 minus pi 4. This will be natural log of pi. Those two terms can be simplified to natural log pi. And we can add a pi over 4 gamma, which will cancel out with the initial one. We're simply left with, simplify everything, pi over 4 natural log of, there was this gamma and no 4 here, so we can raise it to power 4 using properties of exponents, or natural logs in this case, over pi. We can probably bring a power of 2 out. So pi over 2 natural log of gamma squared 3 pi over 4 pi to the 1/2. Let's remember the reflection formula that will help us simplify stuff. Gamma 1/4 times gamma 3/4 is pi over sine pi over 4, which is square root 2 pi. So gamma 3/4 is square root 2 pi over gamma 1/4. So in the gamma squared, there's two of those. Let's use one of gamma 3/4 to write it like this, which ends up with pi over 2 natural log of gamma 3/4 square root 2 times pi over pi to the 1/2 gamma of 1/4, which can be simplified a little bit more to give pi over 2 natural log of square root of the quantity 2 pi gamma of 3/4 divided by gamma of 1/4. I mean, you can use probably some duplication formula to find the value of gamma 3/4 and 1/4. If you find 1/4, finding 3/4 is easy using the reflection formula, but this is where I shall end my answer because this looks nicer with gammas inside the natural logs, and hence we've solved the problem. Thanks for watching, guys. Please send me more recommendations for videos, otherwise I might just do some branch cut integrals or more of these Malmsten integrals. So Thanks for watching. This was Vardi's Integral for you.